Hello students. Welcome to Varun Tutorials. In this video, we will learn about the law of natural growth or decay. We will explain how quantities grow or decay at rates proportional to their sizes, derive the governing differential equations, and solve 4 practical examples step by step. Let's study the law of natural growth or decay. Let x of t be the amount of a substance present at time t. The law states that the rate of change of the substance is directly proportional to the amount available at that instant. This can be written mathematically as dx by dt is proportional to x. First, let's consider natural growth, where the quantity increases over time. The rate of change is proportional to x, which gives dx by dt equals kx, where k is a positive constant. Separating variables and integrating gives dx over x equals k dt. Integrating both sides yields the general exponential solution x equals c times e to the power of kt. Second, let's consider natural decay, where the quantity decreases over time. In this case, the rate of change is negative, so dx by dt equals minus kx, where k is a positive decay constant. Separating variables and integrating gives dx over x equals minus k dt. Integrating both sides yields the general solution x equals c times e to the power of minus kt. In both equations, c is the constant of integration determined by initial conditions, and k is the growth or decay rate constant. Let's solve example 1. The number n of bacteria in a culture grows at a rate proportional to n. Initially, n is 100, and it increases to 332 in 1 hour. Find the value of n after 1.5 hours. Let n be the number of bacteria present in the culture at time t. According to the law of natural growth, the rate of change of n is proportional to n. This gives dn by dt equals kn, which we separate as dn over n equals k dt. We label this as equation 1. Next, we integrate on both sides of the equation. Integrating gives the integral of dn over n equals k times the integral of dt, which yields log n equals kt plus log c. Combining the logarithms and taking the exponential on both sides, we get the general solution n equals c times e to the power of kt. We label this as equation 2. We use the initial conditions to find the constant c. At t equals 0, the initial number of bacteria n is 100. Substituting these values into equation 2, we find that c is equal to 100. Therefore, equation 2 becomes n equals 100 times e to the power of kt. We label this as equation 3. We are also given that after t equals 1 hour, the number of bacteria n increases to 332. Substituting t equals 1 and n equals 332 into equation 3, we get 332 equals 100 times e to the power of k. This simplifies to e to the power of k equals 3.32. We label this as equation 4. Now, we want to find the number of bacteria after 1.5 hours, which is t equals 1.5 hours. Substituting t equals 1.5 into equation 3, we get n equals 100 times e to the power of 1.5 k, which can be rewritten as 100 times the quantity e to the power of k raised to the power of 3 over 2. Substituting the value of e to the power of k from equation 4 into this expression, we get n equals 100 times 3.32 raised to the power of 1.5. Calculating the exponential part, 3.32 raised to the power of 1.5 is approximately 6.054. Multiplying by 100 gives n is approximately 605.4. This is approximately 605 bacteria. Let's solve example 2. In a certain chemical reaction, the rate of conversion of a substance at time t is proportional to the quantity still untransformed at that instant. At the end of 1 hour, 60 grams remain, and at the end of 4 hours, 21 grams remain. How many grams of the substance were there initially? Let Y be the amount of untransformed substance remaining at time t. Since the substance is converting, its amount decreases over time, representing natural decay. The rate of change is dy by dt equals minus ky. Separating variables gives dy over y equals minus k dt. We label this as equation 1. Next, we integrate on both sides of the equation. This yields the integral of dy over y equals minus k times the integral of dt, which gives log y equals minus kt plus log c. Taking the exponential of both sides, we get the general solution y equals c times e to the power of minus kt. We label this as equation 2. Let y0 be the initial amount of substance at t equals 0. This gives the constant c equals y0, so y equals y0 times e to the power of minus kt. We label this as equation 3. We use our first condition. At t equals 1 hour, the remaining amount y is 60 grams. Substituting these values into equation 3, we get 60 equals y0 times e to the power of minus k. Solving for the exponential term gives e to the power of minus k equals 60 over y0. We label this as equation 4. We use our second condition. At t equals 4 hours, the remaining amount y is 21 grams. Substituting t equals 4 and y equals 21 into equation 3 gives 21 equals y0 times e to the power of minus 4k. We label this as equation 5. Now, we substitute equation 4 into equation 5. This gives 21 equals y0 times the quantity 60 over y0 raised to the fourth power, which expands to 21 equals y0 times 60 to the fourth power over y0 to the fourth power. Simplifying the y0 terms gives 21 equals 60 to the fourth power divided by y0 cubed, which rearranges to y0 cubed equals 60 to the fourth power over 21. Calculating 60 to the fourth power divided by 21 gives approximately 617,142.86. Taking the cube root of this value, we find that the initial amount y0 is approximately 85.13 grams. Let's solve example 3. In a chemical reaction, a given substance is being converted into another at a rate proportional to the amount of substance unconverted. If 1/5 of the original amount has been transformed in 4 minutes, how much time will be required to transform 1/2? Let x be the amount of the remaining substance at time t minutes. According to the law of natural decay, the rate of change is proportional to x. This gives the governing differential equation and its general solution x equals c times e to the power of minus kt. We label this as equation 1. Let m be the original amount of substance at t equals 0. Substituting t equals 0 and x equals m into equation 1, we get c equals m, so x equals m times e to the power of minus kt. We are given that after t equals 4 minutes, 1/5 of the original amount has been transformed. This means the remaining amount of substance x is m minus 1/5 of m, which equals 4m over 5. Substitute t equals 4 and x equals 4m over 5 into equation 1. This gives 4m over 5 equals m times e to the power of minus 4k, dividing by m on both sides gives e to the power of minus 4k equals 4 over 5. We label this as equation 2. Next, we take the natural logarithm of both sides. This gives minus 4k equals log of 4 over 5. Multiplying by minus 1 yields 4k equals log 5 minus log 4. Dividing by 4, we get k equals 1 over 4 times the quantity log 5 minus log 4. We label this as equation 3. Now, we want to find the time t when 1/2 of the substance is transformed, meaning the remaining amount x is m over 2. Substituting x equals m over 2 into equation 1 gives m over 2 equals m times e to the power of minus kt, simplifying this gives e to the power of kt equals 2. Taking the natural logarithm of both sides yields kt equals log 2, which gives t equals 1 over k times log 2. Substituting the value of k from equation 3 into this relation, we get t equals 4 times log 2 divided by the quantity log 5 minus log 4. This gives the final expression for time t. Using the approximate values for the logarithms, we get log 2 is 0.6931, log 5 is 1.6094, and log 4 is 1.3863. Substituting these values, we get t equals 2.77259 divided by 0.22314, which is approximately 12.42 minutes, or about 13 minutes. Let's solve example 4. A bacterial culture, growing exponentially, increases from 200 to 500 grams in the period from 6 a.m. to 9 a.m. How many grams of bacteria will be present at noon? Let n be the amount of bacteria in grams at time t hours. For simplicity, let 6 a.m. correspond to our starting time t equals 0 hours. According to the law of natural growth, the population increases exponentially. This gives the population equation n equals c times e to the power of kt. We label this as equation 1. We are given that at 6 a.m., when t equals 0, the initial amount of bacteria is 200 grams. Substituting these values, we find that the constant c is equal to 200. Therefore, equation 1 becomes n equals 200 times e to the power of kt. We label this as equation 2. At 9 a.m., which is t equals 3 hours later, the amount of bacteria is 500 grams. Substituting t equals 3 and n equals 500 into equation 2 gives 500 equals 200 times e to the power of 3k, which simplifies to e to the power of 3k equals 2.5. Taking the natural logarithm of both sides gives 3k equals log of 2.5. Dividing by 3, we get k is approximately 0.3054. We label this as equation 3. We want to find the bacteria amount at noon, which corresponds to t equals 6 hours after 6 a.m. Using exponent laws, we can write e to the power of 6k as the square of e to the power of 3k, so n equals 200 times the quantity e to the power of 3k squared. Substituting the exact value of e to the power of 3k equals 2.5, we get n equals 200 times 2.5 squared. Since 2.5 squared is 6.25, this simplifies to n equals 200 times 6.25. Multiplying these values yields n equals exactly 1250 grams at noon. Note that using the rounded value of k gives 1249.8 grams, while the exact calculation yields 1250 grams. Thank you for watching. If you found this helpful, please like, share, and subscribe to Varun Tutorials. Turn on notifications so you never miss a new video.